when light or any wave passes through two openings, we will get diffraction taking place through both openings. You can see in this diagram here we have monochromatic light, one color light, passing through these two openings in this barrier. You can see diffraction taking place as well. In fact, two diffraction patterns. When these diffraction patterns overlap, we get a phenomenon called? No. Dispersion relates to refraction, not diffraction, right? When these diffraction patterns overlap, we get a phenomenon called interference. Now, we get areas of constructive interference where crest and crest meet or trough and trough meet, but we also get areas of destructive interference where crest meets trough. If we were to be able to see the interference that was taking place from overhead, then we would see a line of constructive interference right here. That would be big crests and big troughs resulting from crest and trough and trough. But right beside it, we would see an area of destructive interference where crest met trough. We would see nothingness there, darkness, the absence of light. But then right beside that, we would get an area of constructive interference, then destructive, then constructive, and so on both sides. But here's the thing. If this is water waves, we can see this fine, right? Easily. We saw a picture of that yesterday. But if this is light waves, we can't see it because the light's not reflecting off of anything. So we have to add something in there for the light to reflect off of so that we can see it. We add a screen. This is our screen right here. This is what causes the light to reflect and allows us to see this interference pattern. If we had, Chase, a bright line right here that we couldn't see, it would form a bright spot on the screen right here. If we had, right next to that, destructive interference, then we would see a dark spot on the screen right here, and a bright spot as a result of constructive interference, and then a dark spot, and so on. So we look at that screen, and we see, as we saw for real yesterday with the laser and the diffraction grating, we would see bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, right? What's another name for the bright spot, by the way? Bright spot aura starts with an M. Maximum. Okay, what's another name for a bright spot or a maximum? Antinode, yes. Bright spot, maximum, antinode, all synonyms here. What's another name for bright spot? Bright spot, maximum, antinode, area of constructive interference. Okay, then the dark spots, dark spot, node, destructive interference. What's the M word that goes with that? Minimum. Okay, they all kind of go together there. We're going to call this one our central maximum, or our central bright spot. We're going to assign a number of 0 to it. First order maximum, or first order bright spot. Second order maximum, and then of course it's symmetrical on the other side as well. Let's label these variables now. Lambda is what? Lambda is the wavelength of the light. Okay, if it's monochromatic light, one color light, it's one particular wavelength of light. Usually visible light, usually 10 to the minus 7 meters. Not always. D, little d is the, what's little d stand for? The distance between the openings. The distance between the openings from the middle of one to the middle of the other opening. That takes care of another variable in both equations. Next, we have L. L, which I'm going to label as a capital L, as opposed to a lowercase, is a distance from the barrier, or the openings, to the screen. So far, so good, right? The tricky ones are x, theta, and n. X, theta, and n. X is, well, x can be pretty much whatever distance I want, from this maximum to this minimum. Or it can be from this maximum to this maximum. Or it can be from this minimum to this maximum. X can be whatever distance measured in meters that you want, as long as n is consistent with it. What would n be in this first case here? going from here to here, what would n be? 1.5. Right, we're going from 0.5 to 2, n is 1.5. What about, let's go this one here, from 1 to 2 on the other side, n would be 3. From 1 to 2 is 3. And what about n right here, from 2 on one side to 1.5 on the other? N would be 3.5. So you're good there. You're good for any of those values of x, as long as your value of n is consistent with your value of x. Theta, that was a poor choice of color. Let's go with orange here. Theta can be this angle measured from the central maximum, central bright spot, central antinode, central constructive interference to the first order, or first order maximum, or it could be to the second order minimum. It doesn't really matter as long as n is consistent. What would n be right here? From 0 to 1, n is 1. From 0 to 1.5, n is 1.5. Okay, make some sense? Okay, let's take a look at these two equations now that we know what each of the variables means, okay? And let me tell you that this equation that we see at the top here, d sine theta, that's the best one. Okay, that's the best one because that is always valid. Always valid, no matter what, no exceptions, as long as you have the angle as measured from the central maximum. The second equation is actually not a real equation. It's an approximation. It's an approximation that works very, very, very well if the angle involved is actually quite small. If theta is less than 10 degrees. If theta is less than 10 degrees, then it's still an approximation, but it's a really good one. If theta is above 10 degrees, then it's not as good of an approximation, so we don't want to use it. It's okay to use this. If you're below 10 degrees, you'll get the right answer. If you're above 10 degrees, the answer starts straying a little bit more from what we should end up getting. Now, I have a little rule of thumb, because to me, like, when they publish our program of studies and they show us, you know, what we got to teach and so on, they say, you know, look, basically, make sure they don't use this if the angle is greater than 10 degrees. Well, to me, when I look at that, it's like, well, okay, so you mean I got to check every time to see what the angle is? If I'm not given the angle, I got to find the angle and make sure it's less than 10 degrees. If I have the angle and it's less than, well, why wouldn't I just use this? And if I got to find the angle to see if it's under 10 degrees, then, well, why wouldn't I just use this? So I have a little rule of thumb that will, it doesn't always help us to avoid finding the angle, but it does most times. Helps us to avoid finding the angle, okay? So here's what I'm going to say is your rule of thumb. This equation will absolutely work if L is greater than 10 times x. So if you take your value for x and multiply it by 10, and L is bigger than that, you are 100% for sure good to go with that equation. Now, if you find that L is, oh man, it's so close, L is almost greater than 10 times x, well, now you got to find the angle. And you might still find it slightly less than 10 degrees, but you got to find it anyways. Okay, a rule of thumb errs on the side of caution. So our angle may be like 9 degrees, even if our rule of thumb doesn't work, but it's better than having to find the angle every single time, right? Okay, make sense? Always, sometimes. Usually it's okay, but we got to do our little rule of thumb check to make sure. All right, let's take a look at a problem. Example number 1 says, Monochromatic light. What's mono mean? One color. You're going to see tomorrow what happens if we have more than one color. It's not a big deal at all. In fact, as much as it might bother you when you see it, like all these different colors, you end up treating it exactly the same way. You just got to be careful of something. Monochromatic light shines through two slits, producing a third order bright spot 9.5 millimeters from the central bright spot. What is that? That distance from the central bright spot. What is this 9.5 millimeters? That's x, right? Look back here, that's the distance from the third order maximum to the middle bright spot. That's the value of x. Now I'm going to convert that to meters. 0.0095 meters. Oh, listen, as soon as I write down x, or as soon as I write down theta, I want to make sure that I write down the value of n to be consistent with that. What would n be here? From the central maximum to the third order maximum? 3, yeah. Now, sometimes we have a little bit of trouble with that, especially if it's involving a minimum. It's a 0.5. Sometimes there's value in sketching it. Central maximum. First, second, third order maximum. Difference between 3 and 0 is 3, yeah. Now, it becomes especially useful to sketch this out if you're talking about, say, the first order maximum and the third order minimum. Right now you can see the benefit of sketching it, right? First order maximum, third order minimum, that would have been, n would have been 1.5 in that case, right? Easier to see when we sketch this out. We're going from 1 to 2.5, so it would be 3.5. What did I say? Should be 1.5. Is that what I said? Yeah. But here we're 3, because we're going from 0 to the third order maximum. Okay, what is this value? 0.15 millimeters. What is that? It's a little d, yeah? I'm going to convert that to meters right now. 0.15 times 10 to the minus 3. I could move the decimal place, but 10 to the minus 3 is easier, I think. 90 centimeters away. That's 0.90 meters, by the way. What variable is that? That's L. We want to find the wavelength. If you look at your two equations that you have, that I wrote down on the previous page, looks like this is the one that I want to use, right? xd over n times L. That's on your data sheet, by the way. Right? Like that fits best, right? Okay, but we got to do a little check because this one's only valid if the angle is greater than 10 degrees. What's our rule of thumb? Is L greater than 10 times x? Is L greater than 10 times x? What's the value of x? 0.0095. Multiply it by 10. 0.095. What's L? 0.9. Is L greater than 10 times x? Yeah, so we're good there. X is 0.0095. Now it's pretty straightforward, right? Times d n and L. And it doesn't have to be in meters, but I would recommend meters for these ones. As long as you're consistent, you can get away with anything. But the units for your answer are usually either nanometers or meters, so I just go with meters the whole way. Yeah. We get 5.3 times 10 to the minus 7 meters. That's our answer. Hey, just a quick little aside. What if L wasn't greater than 10 times x? Then you would have had to find theta. Use the other equation. We don't have theta, so we got to find it. If this is x and this is L, then you could find theta then, right? Tan theta is equal to x over L, and you could get theta, and then you could use that other equation. We don't very often have to do that, but be ready for it in case you do, okay? Okay, I got one more example, then we're going to wrap it up here. Monochromatic light, 589 nanometers. That's a wavelength. I'm going to say 589 times 10 to the minus 9 meters. 2 slits. Second dark spot from the central bright fringe. Theta is 15 degrees. Hey, we couldn't use that other equation even if we wanted to, right? But if we have theta, why would we anyways? What's n going to be? Central bright spot. Second dark spot. Central bright spot. Second dark spot. N would be what? 1.5. Oh, what angle is the third order maximum? Whew. We'll call this the angle of the 1.5. This will be theta 3. Here's what I'm going to do first. This is a tough question. I'm going to say lambda is equal to d sine theta over n. And the only variable I don't have here is d. That gives us a value of d of 3.41358 times 10 to the minus 6 meters. I want to find the third order maximum now. Isn't d going to be the same? Like the distance between the slits isn't changing, is it? So now let's say, what are we looking for here? We're looking for theta this time. So rearrange this to solve for theta. Hold on 2 seconds here, guys. We just solved for d. What would n be here? 3. And what would lambda be? The 589 value, right? You solve for theta. It works out to be 31 degrees there. Does that make sense? That's a tricky one. Hey, your homework for tonight? Oh, you thought you got away with it, but not quite. Worksheet number 19. Good news is, there's 9 questions on that page. I'm not going to make you do all of them. 8. No, just do the first 4. First 4. Worksheet number 19. 1 to 4.